Imagine a kangaroo that is 1 meter away from a patch of grass. However, it can only jump half the remaining distance each time. It is approaching to 1 meter but will never reach it. This example conveys the main idea of a limit.
Sometimes formalities are necessary, as is in the case of the limit. Let us look at the informal definition of a limit. The limit of f of x as x approaches to a value a is equal to a value L if and only if we can make the difference between f of x and L as small as we want by making the difference between x and a small enough.
Here is a graphical representation. Let us look at the formal definition of a limit.
The limit of f of x as x approaches to a is equal to L is equivalent to, for all epsilon greater than 0, there is at least one delta greater than 0, such that the difference between x and a is less than delta implies that the difference between f of x and L is less than epsilon. Here, epsilon encompasses all the as small as we want values that are all the possible differences between f of x and L. And delta encompasses all the small enough values that are all the possible differences between x and a. However, the phrases as small as we want and small enough are not mathematical at all, though this definition might still seem very confusing. So, let me explain this with an analogy. Imagine that you are in a court of calculus, where you are the attorney defending that the limit of f of x as x approaches to a is equal to L. The prosecutor challenges you with the statement: if the limit of f of x as x approaches to a is equal to L, then make the difference between f of x and L less than a value epsilon. I challenge you with an epsilon. Objection. Order! Order! You can counter the prosecutor by finding a positive number delta such that the difference between f of x and L can be made less than epsilon by making the difference between x and a less than delta. In conclusion, epsilon is the challenge and delta is the proof. Case dismissed.